and continued growth at all our locations and facilities. But these accomplishments, as significant as they are only the beginning, the spark for something greater.
Welcome, everybody. We're with the Trine Biomedical Engineering Department, and we partnered with Parkview to give you the Central Line Trainer by Sloan, Griffin, Kristen, and Caden.
So what is a central line? A central line, or central venous catheter, is a small, flexible tube that's inserted into the right internal jugular or right subclavian vein to provide access to the heart. This is for long-term medication delivery, nutritional support, or fluid support, or frequent blood sampling. And you can actually see a central line go in through the right internal jugular on the top there, or in through the right subclavian vein on the right. Around 27 million central lines are done each year, and there's about a 3% complication rate. Some of those complications include pleural puncture, where the needle goes to the pleural membrane surrounding the lungs, arterial puncture, where the needle may pass through the vein and the artery, right underneath the veins, cardiac perforation, where our guide wire is inserted too deep into the heart, infection, or deep vein thrombosis.
So, why are we doing this project? Well, for starters, the central line insertion is a dangerous process, and complications can sometimes even be life-threatening. And currently, there's no real good way for physicians to practice this. So what Parkview currently has to do is they have to switch between two models. So they'll go and do the first half of the procedure on one model, and then the second half on the other model. And as you can see in the picture, that pool noodle is what they use for their second one. So it's not real realistic. And also, other issues that can arise are just with buying a trainer, they're very expensive. They can sometimes have limited uses, and then sometimes they're not even recyclable. So with this model, what our goals are is we want to be able to complete the procedure from start to finish. And the most important thing that we want is the ultrasound guided needle. We also want this project to be reusable and cost effective.
So we're iteration 2.5. Last year, a senior design team started with iteration 2 as Parkview has iteration 1. Last year's senior design team completed a very basic CVC trainer in which they did have a model with the muscular system and then a skin layer, fluid system, and sensors. However, theirs was not overall reliable and did not support a full CVC procedure. As their skin layer and their muscular layer had an air gap between them, they were not able to ultrasound and have any scattering or vessel visualization. Along with that, their tubing system was closed off. There was no way to fill their system or drain their system. When we received their trainer, the reservoirs were filled with debris, and we had to cut the tubing in order to drain it. Along with that, their sensors were not integrated correctly, so they were not testing for the correct things.
Talking to our customer, we came up with a list of product requirements that our product had to meet. So we wanted to make sure that our product was ultrasound compatible, it was more anatomically accurate than the previous model, and then those two complications I talked about, the pleural and arterial puncture, we wanted to introduce sensors to the system that would alert the user when they were making a mistake. Also, they want the model to be reusable and suturable. Based on those customer needs, we developed technical specifications to ensure that we were meeting those needs. So the majority of these have to do with the diameters, lengths, and depths of the vasculature of the neck we're trying to model, as well as the injection force needed to puncture the vein or the top layer of tubing of our model, and making sure that our sensors function correctly to alert the user that they've made a mistake.
To help assist with making sure we got all these technical specifications, we broke our project into 4 main subgroups while producing the project. And these are
the fluid flow system, which is a 3D recreation of venous and arterial flow.
The carton shell, used for aesthetics and also to get anatomical correctness.
And the skin model, which will be ultrasoundable, reusable, and suturable.
And finally, the electrical control system, which drives our fluid as well as our sensing system.
So, beginning with the fluid flow system, as with any other project in the real world, it's the same in senior design. You need some form of model to show that what you're doing will work. So last year, they created a 1D pulsatile flow model, which is Womersley flow that comes from the heart, to show equivalence between the pump and the heart. And you can see that Wormsley flow profile in the right up there, and which was modeled in MathCAD. That's actually the velocity of the fluid coming from the common carotid artery. This year, I wanted to expand the scope to a 2D model of the arterial blood flow and a 3D model of the steady venous blood flow, in the hopes of showing that there is equivalence between blood and water, which would be a different liquid used this year. So I began with a 3D model of the venous system, and you can see there is a model of the right brachiocephalic vein that I made in Autodesk Inventor. I then imported that into COMSOL and applied the relevant boundary conditions, including pressure and velocities that would be seen around that area. And here you can see a heat map of those velocities. And on the left is the laminar flow of blood in that bifurcation. And on the right is the water flow in that bifurcation. And if you can see a difference between those, I commend you, because they're nearly identical, and that's what we were going for. So then I transitioned into a 2D model of the arterial system, which again is Wormsley flow. So right here, I modeled the common carotid artery, and this is not just a rectangle. In fact, this is a cylinder. It's revolved around that center dotted line, and that is a model of, again, our common carotid artery. Using a derivation of 2D Wormsley flow, I applied boundary conditions to the inlet and outlet of this model, and you can actually see the streamlines for that flow profile in real time of when the heart is beating. So on your left, you see blood flow, and on right, you see water flow. To put those in a graph, on the top here, we have blood flow. The top left is the velocity profile at the inlet. The top right is the velocity profile halfway through the common carotid artery in blood. And then in the bottom left, we have the inlet velocity profile using water, and the bottom right is the halfway point velocity profile using water. So between the models, we've seen near equivalent velocity profiles for everything that I've modeled, and we've seen that the flow is not noticeably affected between the lipids. So moving on to the physical part of our fluid flow system, last year's system used a couple different sized fittings and different sized tubings and different types of tubing. So the first thing we did was we limited that down to one type of tubing, one size of tubing, but it was succinct around everything. So this is one of our earlier models. On the left, you see the arterial system, and on the right is the venous system, to test those different fittings together. After I did some experimentation, we went ahead and made two simple models here of what the system should look like to make sure that we can fill and empty it with ease. So the top is our skin model. That's the big blue L. On the left is a cylinder for our reservoir. In the center is the pump with the directional flow. And on the right is our pressure gauge. And again, our arterial system is on the left and the venous system is on the right. These are the different components that were used in the final iteration. On the left, you see a reservoir suspended by clamps, which is drilled into the underside of our cart. Our new Y-splitters, the 5/16 inner diameter, 7/16 outer diameter silicone tubing we used, and then some of our pump stands. And then here's what our final system actually looks like. The left is a front view, which is kind of hard to see, and the right is a side view, which kind of illustrates our design better.
So next we will talk about the cart and the shell. So the cart was another one of those big improvements that we made from this year to last year. Last year's project sat on a flimsy acrylic board, and this caused problems with transporting it. Not only was it awkward to transport, but it was also dangerous for the device itself. So we decided to put the whole thing on the cart. And the cart allows us to hide a lot of our wiring and tubing, and we only had to make a few modifications to it, such as drilling holes for tubing and laser cutting a hole for the plugs to go through. Along with the cart, we also upgraded this year's shell. So last year's shell, as you can see in the image to your left, and then also on the table, it was big, it was bulky, and it was also fragile. And another major issue with it was that the actual skin mold didn't really sit in necessarily the correct place for the procedure to take place. So we decided to upgrade to this hard plastic shell, and we had to make a few modifications to it, such as cutting out an area for our skin mold to sit, drilling holes in it for tubes to go through, and then also 3D printing clips so that way when the shell is on top of the cart, it's stationary.
So our next big upgrade was the skin model. To start off, we looked at last year's model in which their mold in which they poured their ballistic gel or the muscular layer, it was large and bulky. It's sitting on the table and in the picture. It's heavy and it's very hard to replicate their skin model that they created. So it was hard for the guest to use. And so we shrank this system down because their ballistic layer was very thick and had excessive amounts of ballistic gel that's not the same thickness as the human anatomy. So we shrank it down to be more anatomically correct. Along with that, their tubing was cut out to be inserted into the ballistic gel. So we wanted to insert the tubing directly into the mold. So we poured the ballistic gel over top of the tubing. To do that, we needed the mold to be able to be heat resistant since the ballistic gel is poured in at a temperature between 220 degrees Fahrenheit and 250 degrees Fahrenheit. After research, we determined that polycarbonate was our best option for designing our mold with. This was difficult to print with, but as soon as we got a bamboo printer, we were able to print successfully. And with that, we also had plugs for where the sensors will integrate in between the vein and the artery. So those plugs go in when we pour the ballistic gel. With that, last year's mold or the skin and the muscular layer were very thick, as you can see in this image, and you could not actually ultrasound them at all. Their skin was Elena, a former alumni's model, and then the ballistic gel was a combination of ballistic gel, but to hold their tubing in last year, they actually used hot glue and super glue to hold it still. So that made their ballistic gel unusable for this year since there was a lot of additives in it that we didn't want. So with that, we kind of restarted. So for the skin layer, we need it to be able to be sutured, but still ultrasound. So silicone is the best option for suturing, but if you have it too thick, you can't ultrasound it. So we kept it thin, about 4 millimeters thick, and we embedded a nylon mesh within it so that you can suture it and the sutures are held in place. And the specific type we used was Dragon Skin 20, which is best replicate of the human skin. After that, the lower layer is the muscular layer or Humimic medical grade gel number 4. With that, we embedded glass microspheres for scatter additive so that when we ultrasound it. We first tested this on a mini model here, and then we took it and upsized it to the L or the neck region to the full-size model. With that, we were able to complete over 3 full CVC procedures without any complications or problems. And it's easy to replicate since you can just simply take it out. It's also reusable because your ballistic gel can just be remelted to add new tubing after too many punctures.
And our final subsystem is the electrical control system. So the first thing we did when developing the electrical system was make a circuit layout centered around our primary microcontroller, which is the Arduino Mega 2560. We then also mapped out our different devices, such as our 12-volt cooling fan and our different pumps. And then finally, we added in a legend labeling different wires as well as resistors that are included throughout the circuit so that this can be easily followed for recreation. So propelling the fluid flow throughout our system, we have 2 primary pumps. We have a diaphragm and peristaltic pump. The diaphragm pump is hooked up to our venous system, and that propels at a constant 10 millimeters per mercury output, similar to what we should see inside the vein. The peristaltic pump is hooked up to our arterial system and runs at a 4-stage on-off sequence that mimics the arterial system's lub-dub that we get from our heart.
We designed a circuit box to house all of the electrical components on the side of the part. So it's fabricated through PLA as a fan port, button ports, a place for the LCD to be seen, and then it actually has holes for the wiring on the backside.
Embedded into the front of the circuit box are our 5 primary control buttons as well as an LCD display. So the power button in the middle turns on and off the device, and then the venous toggle systems will turn on and off the diaphragm pump. The heart rate buttons will increase or decrease the beats per minute that we're seeing from that lub-dub, allowing for the customer to control exact system parameters for different scenarios. These parameters are then displayed on the LCD as our venous pressure, our arterial heart rate, and our alert status. And then if the system is turned off, the LCD will shut down to signify there is no system on. Integrated with this, we also have 3 primary sensors over the different complication sites discussed earlier. These sensors are protected by PLA force plates to help make sure the needle does not damage them for continuous reuse. When the force plate is hit by the needle, it triggers an alert, sending a signal to a buzzer, letting out a tone that we will demonstrate later, as well as sending an alert location on the LCD, letting the practitioner know where exactly they triggered a complication.
So now we'll get into our testing. One of the first tests we wanted to run, which is most important to the customer, was ultrasound testing. With the ultrasound testing, we wanted to see a scatter surrounding the tubing along with vessel visualization. We did this on 5 different samples and it was overall compatible with it all.
So for our FlexiForce testing, we're able to adjust the values of how much force they can actually set the buzzer off on. So our main goal was to ensure that there would be no false positives and that you would also not have to hit the force plate too hard. And what I mean by false positives is that we don't want the buzzers going off just from the needle sticking thin through the skin and going into the vein because it will pick up some force there. Rather, we want it just as it touches that force plate to go off. And so we did 10 tests on each of the 3 sensors and got them to work all 10 times.
Next, we piggybacked off of last year's puncture testing, in which a 23 gauge needle was put through the silicone tubing at a certain using an Instron machine, and we wanted to make sure that the force going through them was consistent. So over 9 trials, we met what was expected from the ASTM standard.
We also had to confirm the device had a long-term usability. So to do this, we ran a 10-hour leak test, making sure there were no major ruptures in the tubing that would inhibit device function. And the only leakage we saw was from the puncture site, which is to be expected when you're stabbing the tubing with a needle.
We also ran a suture test to determine how many sutures can be placed in the exact same spot before tearing occurs. So the standard is 6, and we completed 6 sutures on the first 4 samples in the exact same spot. And then we completed 10 sutures in the final one just to see the long-term, and all of them were successful without any wear or tear on the skin model.
So originally, we were going to use a metal detector to detect it when the guide wire goes past 30 centimeters. However, we ended up finding out that our metal detector wasn't strong enough and the guide wire was just too thin for it to be able to be picked up. Luckily, though, this was only a secondary requirement due to the fact that you can lift up the shell and see exactly where the guide wire is in the tubes, and also on the guide wire, it has specific markings for how deep it's already gone. So, a little bit of background on how to actually perform a central line insertion. The first thing that you're going to want to do is you're going to want to get the proper PPE on, such as gloves and a face mask. Then you're going to clean the area that you're doing the procedure on, put a sterile cloth or drape over them, and then you are going to take your lidocaine and you're going to want to insert that in 2 spots. The first spot is where the actual catheter is going to be inserted, and then the second spot is where you think that you're going to make your sutures to hold the catheter in place. After this is done, you're going to take your needle and you're going to insert it into the vein. This is done with ultrasound guidance. So on most machines, or I guess on newer machines, they'll have the Doppler effect, which will show your vein is blue and your artery is red on the ultrasound, and then also a center line. And the center line is just a line straight down the screen showing you where the center of your probe is. So you will use all those tools to insert the needle right into the vein. Once you know that you're in the vein, you will take the guide wire, put it through the needle, and insert it to the correct depth. And it's important to be holding onto the guide wire at all times because that can actually be sucked into the body. And so after this, you're going to take the needle out while keeping the guide wire in. And then you're going to take a small knife, make a little nick right next to the guide wire. And then you're going to take a dilator, which will just make the hole a little bit bigger. You're going to dilate the hole, take the dilator out, and then you're going to take your catheter and put it in using through the guide wire. After this, you're going to take the guide wire out through the end of the catheter, and then you're going to suture the catheter in place.
So now we're going to test it on Griffin. I'm just kidding. We have a live demo.
Please keep in mind that we are not trained professionals by any means. The actual people would perform it by standing on this side, but for visualization of this, we're going to do it from the opposite side.
So as you can see, we can see the vein right here, and then underneath that is the artery. And as she actually inserts the needle, you'll be able to see the needle once it goes through there, and I'll point that out.
We do not have the Doppler effect on this one or any of the.
Even.
We do not have the best ultrasound for this, but
Yeah, you can kind of see the needle poking through right there.
and if I were to draw back, I could get blue out of this right now. And then the next steps to this would be to use this guide wire. This is the guide wire. It's super thin in all of it. And then this is what the catheter looks like. So it's going to create a decent size hole overall. Now Sloan's going to try out a sensor.
So here's how the sensors work. The machine has to be on. And then I'll check the pleural membrane sensor. So let's just say I really messed this up and I'm about to hit the pleural membrane. See the buzzer go off right there? And then that's the same way that it works for both the arterial systems.
Next, we're going to show a video of the rest of the demonstration. So this would be pulling the fluid out. You can see the liquid going in. This was before we added coloring to it. The next step is adding the guide wire through. Following that, we remove the needle. And then we would add a nick so that we can put the dilator in next. Following the dilator, we put the guide wire in, and then you remove the guide wire, and then you suture it in place. We're obviously not professionals at suturing, so this is just to show that it does have the strength to pull.
Moving on to the verification of our technical specifications. So using the test methods listed on the right side, we met all of our technical specifications, except for the mold depth, which we decided to change halfway through because the old model was actually much deeper than is necessary. So to save on cost of ballistic gel, we made it shallower, and that's also based on the depth of the common carotid artery. So we don't need all of that extra distance underneath it. You can set it on the PLA mold itself and actually make up that distance yourself.
Yeah, and on to the verification. So our model is able to complete the entire procedure. We have sensors that give real-time feedback. We have separate arterial and venous flow. And also our model is able to be reused around 6 times before we'll need to change out. The tubes will be the first thing to go, and then probably the skin. But the ballistic gel can all be recycled. And then customer feedback. Our customer really, really liked this project. He had some great things to say about it. He's very excited for the trainees to be using it this summer, and he was very, very satisfied with us. And then on top of that, at the Senior Design Expo, we actually had a nurse try out the whole procedure on it, and she had some great things to say about our skin and tubing. She said that it felt just like regular skin, and she got the same pop when entering into our vein as you would in a human's vein.
So some future improvements that could be made to this device include adding in a inductive proximity sensor to help detect that guide wire when it goes too deep. So where our metal detector failed, this would most likely succeed, and that would help alert if there was cardiac perforation, so the guide wire entered the heart. We would also like to have a stronger pump system, so a stronger arterial pump would allow us to see that arterial blood pressure value that we were looking for, as well as a AC venous pump would allow us to have various ranges of venous blood pressure instead of a set value. Finally, we'd like to see some increased functionality by adding in an ECMO device as seen in the figure, which would feature a realistic heart that would beat with our arterial blood lub-dub effect.
Yeah, so these are our total hours broken up by fall, spring, and then our totals. We all put a lot of time in this project, and we're very proud of how it turned out. And then our first semester Gantt chart just to help us keep us all on the same page and keep us on track. And then the second semester Gantt chart, same thing, just helped us let us all know when we should have our individual parts done and when we should be combining them all together.
For the project's budget, we were given a $1,000 maximum budget from Parkview. And of this, as a team, we spent $850 on all the different various systems inside the device, with a final cost with the different donations of $946.76.
So the team would like to thank the following people who contributed to our project. Of course, Trine University and the Parkview Muro Center for sponsoring and letting us use their resources for the project, as well as Dr. Gerschutz, Dr. Watson, Dr. Gong, Dr. Patton, Emily Wall, Logan Krish, and Jack Stover.
In conclusion, we were successful in building an all-in-one trainer so Parkview doesn't have to alternate and use a pool noodle. The trainer is reusable and it's easy to replicate. We gave them user manuals for how to recreate things. There is an accurate fluid flow system. It is anatomically correct and is more of the neck region than previously. And it has live feedback within the sensors. And the entire system is on a cart, so it's easy for Parkview to take it up and down since they have a training lab upstairs and downstairs, actually.
So thank you. If there are any questions, we'd love to take them at this time. Yes, the handsome man in the front.
That was awesome. You guys did a really good job presenting. Very professional, and you guys clearly knew what was going on. My question is, I know most of the other BME projects did not have any prior or previous projects. Do you think having a previous group working on this was more of a blessing or a curse?
I would say it's more of a blessing because I think it's a whole lot easier to look at something and say what was wrong with it rather than start something completely from scratch. And then also another great benefit that we got is we had all the PowerPoints to go off of and the papers to go off of, and we even used their previous testing. So I would overall say that it was a benefit.
It was definitely a blessing in some places, and then in other places, it felt a little bit more hindering with inheriting tubing and stuff. We originally assumed we could utilize that without having to buy our own, but then we found out they hot glued it and completely sealed it off. So we had to replicate new tubing systems as well as their old circuits.
I have a question from John in the chat here on Teams. What is the cost per insert?
What is the...
What is the cost per insert?
Is he referring to a professional insert or our model? So professionally made inserts can cost up to $1,000 per replacement.
Sorry, he added for this model.
For our model, the only thing you have to recreate is the silicone top layer and do new tubing, and it's probably like $20 max. You can buy the silicone, you can buy like the little containers of it, and I think I've done 6 different silicone things and they're $30, and then tubings.
It's like $20 for 30 feet of tubing, and you only need to replace less than a foot?
So maybe like $8.
Vanessa.
Great presentation, guys. If there's one thing you can pinpoint that was your personal favorite aspect of this project, what would it be?
I think for me, it was seeing the customer after he saw the official model. He was so impressed and had so much excitement from seeing the official product and seeing it ultrasound as well as it did. It was so fun to see like John's excitement for what he can do with the project moving forward and what physicians can do with it.
Yeah, I would say it just all came together really nicely at the end. Like the cart was sort of, it wasn't last minute, but it wasn't planned out from the very beginning. And I really think that it kind of tied the whole project together and it made it look real nice and sleek.
I really liked being able to work on so many different types of systems and kind of merging them all into one. I learned a lot about fluid flow systems than I had known before, and I even got to learn a new software of how to analyze them. So that was really awesome for me.
My favorite aspect was probably the fact that it was our first actual long-term project with a customer. So we've had a lot of projects at Shrine where it's a semester long, couple weeks long, and those are a lot smaller. Where this project, we were given a list of things we had to hit, and then a longer frame to make sure we got all those requirements and also see our customer happy at the end.
So you mentioned at the beginning of your presentation that the last model, like the previous group that did this, they really had an issue with an open system and the air affecting the ultrasound, I believe. So is it a concern to have some air bubbles in your tubes right now, or could you benefit from putting more like fluid in?
So their air was actually between the silicone layer and the ballistic layer. So when you ultrasound, they didn't adhere super well together. So there was an air gap. And when there's an air gap when you're ultrasounding for the true model to see the tubing, then you couldn't see anything since they didn't adhere together. So we poured the silicone directly on top, whereas they kind of had like a pre-made skin that they set on top, so they didn't adhere. That was more the air gap that they had rather than the tubing.
You are also correct in saying that having some air in the fluid system is not a good thing, but that's why we do have air bleed valves. And when the system is running, it's pushing fresh liquid up through the model, so there's not air gaps when it's running, which is really nice.
Question from Jenna in the chat. What feedback, if any, did you get from healthcare professionals during your process?
Yeah, the one piece of feedback that we got was at the Senior Design Expo, when we had the nurse actually try this out, and she pretty much just said that our skin model felt like real skin, and the tubing gave the same pop that you would get when you puncture a vein.
And if this continues to be used as expected, we'll hopefully have some more feedback from actual trainees, residents who are using it. So.
All right. So first of all, great job, guys. But this is kind of similar to Maddox's question, but building off of a project that already been started, how did you kind of change your whole process of your product or project compared to if you would have started it from scratch?
So to begin with, they had a very nice idea of what they wanted done, but the individual subsystems didn't really do a good job of meeting those goals. So we really tore apart every individual subsystem and rebuilt them up with the same goal in mind.
I have another question from the chat from Gavin. What was your process ensuring the water sufficiently imitated the viscosity and flow mechanics of blood?
Yeah, so this is a very targeted question. I like it. So blood is a non-Newtonian fluid. So I used a Caro model, which models the effective viscosity at any point. There's a couple different things that go into it, but that's the model I used.
Hello, guys. Great presentation. The past two presentations we've heard from the BME projects have been for an individual customer. Do you think since you've done it for a company, yes, you've had a point of contact, but since you've done it for a company and to help maybe nurses in general, how do you think that's been different?
I think that's more we have to look at the long-term use and being able to use it over and over for several different positions so that they can use it as a true training model and for them to be able to potentially make additional ones of these because when they do their training, they have 4 different stations. So ideally, they would like probably 4 of these carts. So being able to remember that they're going to have to recreate this likely rather than just one simple model as only one replicate.
And piggybacking off of that, Kristen did a great work on showing the manufacturing process. There's a lot of documentation that she put in so that they can redo it. Same with Griffin and Sloan on the coding and all of those systems. They have step-by-step instructions for how to actually reset the sensors and how the code works. So, yeah.
I'm just gonna do one in the chat. First, someone said, as someone currently training to insert central lines, I'm incredibly impressed. I feel a model like this will be an asset to physician assistants. nurse practitioner, and physician in the field. But then someone else say, are you able to take pressure readings and adjust within the vessels?
I guess this is me. Yeah, so there's a pressure gauge. Well, there's two pressure gauges, one for each system, and they're actually located just after the pumps, under on the first tier of the cart. So we don't have any pressure values from the actual inside of the skin model itself, but those gauges could be moved up if that's necessary.
Excellent job. Last week when we visited at the poster presentation, we talked about the limiting factors of your ultrasound not having color flow. And so since then, I've been stewing on what would be a way, and I actually think air may be that way to show up an ultrasound. We do microbubble assays when we're looking for shunts between arteries and veins, and you might be able to run microbubbles through that system to pick up an ultrasound and actually give you a little bit more scatter to give you a better image on your ultrasound. I don't know. Something I thought about since last week.
I know Parkview also has a lot higher quality ultrasounds than we have here. They have the Doppler effect on theirs, and they're really excited to try it with the Doppler effect for ours. We just haven't taken the full cart there since it is larger.
Well, thank you all for joining us. This is the end of our presentation. Appreciate that you joined us. There will be another senior design presentation here at 3 p.m. So yeah, thank you all for coming. We really appreciate it.
Trine University continues to boldly climb to new heights of success. We have record numbers of students, new academic programs in areas such as health professions and engineering that meet the needs of businesses, organizations,